Greetings, everyone. Welcome back. It's time to talk about partial derivatives. What a partial derivative is this same idea as the derivative you've been doing, except now we're talking about a multivariable function, so I can choose either x or y as the independent variable that I wish to take the derivative with respect to. Okay, so you might think, well, since it's a multivariable function, when I do a derivative, shouldn't I just do the derivative of x and y at the same time? And that would be nice and all if you could do that, but nothing in mathematics ever works as a big group like that. You always need to break it up into its individual measurements and then find a way to bring all those measurements back together into something useful. For example, distance between 2 points. If you measure a distance along a single axis, it's easy. But if you want to go between 2 points in a plane, you need to measure the run and the rise and use Pythagorean theorem to make your distance formula. Same thing in 3 space. It's just, more dimensions. Okay? So same idea with derivatives. Just because I have 2 variables doesn't mean that I should take a derivative with both variables at the same time. In fact, that would be kind of messy and hard to decipher. So here's what we have. We have partial derivatives. Here's our original definition of derivative from Calculus 1, right? I'm using the difference quotient version, and I've written some of the terminology that you're accustomed to seeing. D over dx is an operator, derivative acting on a function, and f prime is the derivative function, right? And its limit as h goes to 0, f of x plus h minus f of x over h, where x is my independent variable. So a partial derivative looks sort of like d over dx, right? But it's this little curly d. What that is a lowercase delta. That should make sense, right? Because the uppercase delta we typically use for measure of change, right? The triangle times y is delta y, change in y, something like that. So the lowercase delta is what we're using here. D over dx, basically. Same setup, right? But when it's curly like this, we mean it's partial, meaning there are going to be more variables than just x, but everything else besides x should be treated like a constant. And that's the key to partial derivatives here, okay? All the other variables are being treated like they're constants. They're not allowed to change while I'm doing the derivative with respect to x only. They're not treated like functions of x either. They are constants. Okay? So it's not like implicit differentiation where you're like, oh, let me do derivative of x, but I still get a y and a y prime and all that other stuff. No. They're not functions of each other. Y and x are both independent variables. So I'm freezing one and letting the other change. And then vice versa, if I go down to partial with respect to y, I freeze the other and then let the second one change instead. So they each get their own independent version of the derivative. Okay? So I use the squiggly d's for partial derivative of a multivariable function. And then just like f prime, the terminology here is f with a subscript of x. Because prime wouldn't make sense, I don't know which partial derivative you did, right? So we use f sub x. And here's what it means. I'm still doing a limit as h goes to 0. That's like your delta quantity, right? And what I'm doing is I'm adding it just to x. You see, x is allowed to wiggle, but y is still there. In other words, I've picked a value for y and it's held constant. It doesn't change between the two values. So notice it's really the same derivative, f of x plus h, f of x over h. You just have y sort of in there along for the ride. Vice versa, same thing for partial with respect to y. F sub y is the derivative there. Limit as h goes to 0. Notice x is held constant. So I have y plus h minus the y version, and then it's over h. And that's a partial derivative just in the y direction. So to give you a visual of what's going on here, imagine I have this parabolic cup here, right? The paraboloid, an elliptical paraboloid. And imagine I pick a y value and just hold it constant. So what that's the same as doing is if you have your paraboloid, imagine taking a plane that just is parallel with the xz plane and hits the y-axis only, and it slices into your paraboloid. You would get a parabola shape from the slice, right? Like this. You would get a parabolic slice, but the y is being held there. But x is still allowed to move in and out along that plane, but it also has to stay with the surface of the function that you're dealing with. So you do the slice on the paraboloid and you get this parabola inside of it, right? This parabolic slice. And as x moves in and out, right, the z value changes along just that curve. So when I do a partial derivative, what I'm getting is the slope of the tangent line to just that curve, not the whole surface, just the curve that represents the slice that we're given. So after I pick a value of y, it slices and it turns it back into a 2D curve, right? And then I can talk about tangent lines again, and that's what derivatives are the slope of. So let's get an actual example here, and then also I'll draw it in GeoGebra for you right after. Notice here I have the function f of xy equals 15 minus 2x squared minus 5y squared plus 3xy. And I know you recognize everything up into that last term. It's still an elliptical paraboloid, right? The elliptical part comes from the double squares and both being negative. The 3xy is just a term that takes the ellipse that's in the bottom and it rotates it. Okay, so instead of being lined up with the x and y axis, it's going to be rotated a little bit into the quadrant, and it'll be ovular, into the quadrant. Okay, so it's still an elliptical paraboloid. I just threw that in there to make the derivatives a little bit more interesting. Okay, so what is f sub x? In other words, the partial derivative of x, of f with respect to x, right? Okay. So that means pretend y is a constant. Y is not a variable. Y does not change at all. So I treat it like a constant. So derivative of 15, 0. Derivative of negative 2x squared with respect to x, that's negative 4x, as you would expect. Derivative of 5y squared, that's a constant, 0. Derivative of 3xy. Now remember, y is just a number. What's the derivative of x? 1. And then any multiplied numbers follow along. So I have 3 times 1 times y, or plus 3y. So there's my partial derivative of f with respect to x. Okay, let's do it again. Partial derivative of f with respect to y this time. Okay, so 15, of course, derivative of a constant is 0. X squared, but it's with respect to y, 0. I'll have negative 10y. And then over here, derivative of y is 1, and then any multiplied constants follow, 3x times 1, so plus 3x. All right? Now, of course, as usual, these are multivariate functions. I technically picked a y value in the x derivative to hold constant, but I didn't actually say which number it was yet, right? I just said hold y constant. But when you actually feed me a point, now that's something. I'm saying I want to hold y constant at 1, so that gives me the plane to slice. And then if x is 2, I'm saying where on the curve I want to do the tangent line at, right? The slope of the tangent line. Okay, but in any case, I'm just going to plug in 2 and 1. That's going to give me negative 8 plus 3, which is negative 5. Okay, and same idea here. If it's f sub y, picking an x holds x constant, slices into the graph, gives me that cross-section, parabola in this case. And then it's saying y equals 1. I'll go along and see where does that tangent line actually exist along that curve. So I'll plug in 2 and 1 here. That's going to give me negative 10 times 1 plus 3 times 2. So negative 10 plus 6 is negative 4. So I hope you weren't expecting those to be equal. They're not supposed to be. We're talking about the rate of change in two completely different directions. This is how we distinguish on a surface what would happen if I change this direction. What would happen if I change just in this direction? So it's individual dimensions. And then, as I said, the way math works is you do your individual dimensional analysis. And then later on, we talk about a way to bring them back together. A couple of sections from now, we'll talk about how to use these two measurements together in an overall vector type of derivative. Okay? Here's another question that can come up. What are the equations for the curve and its tangent line that are associated with f sub x at 2, 1? The partial derivative of f with respect to x, right? At 2, 1 was negative 5. But what are the equations for the curve and the tangent line associated with that particular measurement? So remember what we're doing here, since it's the x partial derivative, we're saying that y is constant at 1, right? So we're gonna let y be equal to 1 held constant. So let's label that, right? So I'm talking about curves in 3 space, right? It's a curve that's the intersection, and the tangent line is also a curve in 3 space. Both of these are going to need parametric equations. Well, good news, I've already got the y for both of them, because y is constant, right? Okay, the next thing I need is the point on the surface that we're questioning here. So I need to calculate f of 2, 1. Right? I need f of 2, 1 so that I know what point the tangent line is hitting and what point the curve is going through so I can create the equations. So f of 2, 1 is 15, minus 8 is 7, minus 5 is 2, plus 3 times 2 times 1, 6, so 8. F of 2, 1 is equal to 8, right? So I found the point 2, 1 in my domain, and then I plugged it in, and my z value is 8 up on the surface, right? So I found the point on the surface, okay? Next, we want to find the slice where the y being held constant hits our surface, and what kind of shape that's going to give us. Well, we already can tell it's going to be a parabola, right? And the actual equation is pretty straightforward. It's like doing this. I'm going to have z is equal to f of x, 1, like that. See, I'm letting y be held constant at 1, right? Okay. And so this is just going to be a function of x, basically. Right here, I've got 15 is still 15. And then minus 2x squared minus 5 times 1. So that's minus 5, right? 15 minus 5, I'll just go ahead and fix it right here. That's 10. And then plus 3 times x times 1. So plus 3x. All right, so I found an equation, but that's not going to work for what we need. All right, remember, things in 3 space, if you're drawing a curve, have to be parametric equations. What I've done is I've shown you the relationship between z and x that gives this parabolic shape. So if I were looking at a plane and it was the zx plane, well, then this would be enough. But that's not what we're doing. we're in three-dimensional space, and I have a curve just whipping through 3D space. I need a parametric equation, okay? So easy enough. I've got a relationship between z and x. So my curve, I'll call it C, is equal to the set of parametric equations where x is just the variable t, y is held constant at 1, and z is equal to, well, x is just t, right? So I have 10 minus 2t squared plus 3 times t. So there's the intersection curve, right? Now, at the point 218, right, because that's the point on the surface now, I have 218 is also on this surface, right? Because if I put 2 in for t, right, that's the output that we're going to get. Yeah, 218. So I have the curve and the point 218. Now I need to know what's the equation of that line that's tangent to it, right? Okay. So that's easy too. I know the slope of the tangent line just in that direction is -5. Okay? So just in the x direction with z, while y is being held constant at 1, at that point is -5. Just at that point and just in the x direction. Okay? So here's my tangent line. I'll call it t. X is still my variable, right? Y is being held constant. And z has to be equal to a tangent line. Well, remember how we do lines, right? I have to add the original point to some sort of vector, okay? Well, the original point is 218. I've already got the 1 for the y. To do the 2 for x, I'm just going to add 2 here. And for z, I know the slope has to be -5t. And then I have to be at the correct point, +8. So look, right here, this is going to be the equation of the tangent line right here. It goes through the point 218 when t is 0, right? And when t is 1, x changes by 1 like it's supposed to, because x is the variable changing by 1 every time. And if I let it go up by 1, the slope -5 goes in the proper direction here and starts adding or subtracting to the z value. Okay? So I've got my curve and I've got my tangent line. That's what it was asking for. So now go take a look at what this looks like in actual 3 space with GeoGebra. All right, here's that function graphed in 3 space. Right? Here's the 15 minus 2x squared minus 5y squared plus 3xy. Like I said, it's the elliptical paraboloid, and notice it has been slightly rotated so that the oval is not lined up with the axes anymore, and that's because of the xy term. Alright, the point in question was 218. There it is, located on the surface there. Right, you can see 2 and 1, right? And then it just comes up 8 from there. Notice the z scale has been squished down a little bit. That's just to make this thing fit better on here. That's all. Let me zoom in a little bit more for you too. Okay, the curve that we said we found was x equals t, y equals 1, z equals 10 minus 2t squared plus 3t. Okay, so then this is that curve. Notice it fits exactly on the surface because it's a set of points from that surface. And it's exactly the set of points that contains the point that we are wondering about. Also, look at what value of y it's lined up with right here. You can see it's lined up with y equals 1. If I were looking at that plane, that would be a line straight through there. So, from the xz plane, watch if I turn off the surface, and then if you were in the xz plane, right, this would be your calc 1 right here.
This is the xz plane, and you're just graphing a parabola, and I'm going to end up doing a tangent line right here, which is, remember the slope was -5, right? It is actually decreasing here, you can see. This is the xz two-dimensional look view of it. But this is what's actually going on, right? I've got the surface in 3D space, and I've only been allowed to follow this path. That's what happens when you set y equal to a constant. I can only walk on this path of the surface. And at this point, the line that we found, t plus 2, y equals 1, z equals -5t plus 8, is the tangent line, completely lined up. As you can see, it's lined up in that same direction. But from the xz plane, you can see it is the -5 tangent line there. Okay? Now I know we didn't calculate it, but let's look at the other direction so that you can see the difference. There's also a curve if you set x equal to the constant value of 2. And this is the slice that you get from doing that. And on top of that, it also has the tangent line that goes like this. If you were looking at the YZ plane, notice you get the parabola, and this is the -4 tangent slope that it accompanies it. In 3 space, this is the tangent line in the y direction, while x is being held constant at 2. Okay? So what happens is we can actually put these two tangent lines together here, and you can see the kind of tangents that you get just at this point. If I am on this point and I want to move just in the x direction, then I would follow a path of the blue line. If I was at this point and wanted to follow just the y direction, then I would follow the path of the green point.
Time to practice partial differentiation some more. Okay, so let's take a look at a of xy here is 5 times ln of x squared plus y squared. And don't forget, all of the derivative rules that you've learned up to this point, all of the laws that you've invoked, power rule, the individual chain rule, product rule, quotient rule, all of those things are still valid when doing these derivatives, because you're still honing in on a single variable, basically giving it its own universe of derivatives, while the other variable is being held constant. Okay, so here, let's say I want to do the partial derivative of a with respect to x, right? A sub x. Okay, so then I'm going to look here. Basically, I'm going to see y squared as just some number. But then I'm still going to act like I have ln of a function of x. So I've still got my 5 times 1 over x squared plus y squared, because, you know, derivative of the ln is going to be 1 over the inside, times the chain rule. Now I've got to do the derivative of the inside piece, which is going to be 2x. So all together here, my a sub x is going to be 10x divided by x squared plus y squared. And a very similar situation for the partial derivative with respect to y. A sub y is going to be equal to 10y over x squared plus y squared. Because again, I'll still be taking the derivative of the ln function with something on the inside, and I'm going to do 1 over that x squared plus y squared there. Okay, but the inside derivative with respect to y then becomes the 2y times the 5 that follows. So they're very similar, right? But you can tell the one little difference that they've got. All right, next. I've got b of xy is equal to x squared times tangent of 3x plus 2y quantity. Okay, so let's do the partial derivative of b with respect to x. So that's partial of b with respect to x. This is the other way we write it, right? Let's get a little bit of practice doing the terminology both ways here. So with respect to x, I'm noticing I have the x squared times a function that also has x in it. So this is going to be a product rule here. I'm going to take the derivative of the x squared first. That's going to give me 2x. And I'm going to leave the tangent alone. Plus, I leave the x squared alone times the derivative of tangent, which is secant squared of, and notice I'm leaving the inside alone, there's a chain rule there, times the derivative of the inside, which is just the derivative with respect to x. So in this case, that would be 3. So I'll just pop a 3 in front right here. And then there's my product rule for that one. I don't really see a lot in common other than maybe the x's. The tangent and the secant aren't going to factor out. So really, in this case, I would leave this derivative in this format, unless there was something specific you were looking for. Okay, partial of b with respect to y. Well, this time, the only y that's here is inside of the tangent here. So I'll just be doing the derivative of this piece. The x squared is a constant, and it's multiplied. So I'll just be doing the derivative of the tangent this time. The x squared is along for the ride. Derivative of tangent is secant squared 3x plus 2y. And then a chain rule. Derivative of the y portion right on the inside is just the 2. So I'll throw a 2 in front here times that. And then there's my derivative with respect to y only. Okay? Now, of course, just like in your other derivatives, you can have higher order derivatives, which is to, do your second, third, and fourth derivative whenever you're in a single variable situation. But talking about higher order derivatives in a multivariable situation means that not only do you have something that you would call a second or third derivative anymore, but you also have the combination derivatives. So you can have, say, your second derivative with respect to x by doing the partial of x twice. So you'd have x. Or same thing, if you do the partial with respect to y twice, you'd have fyy. So those are kind of like your second derivative, your pure directional second derivatives, okay? But you've also got the combo second derivatives. You can do a partial of y derivative on something that you've already done a partial with x on, or vice versa. Do a partial with respect to x on something that you've already done a partial of y on top of. And I want you to notice the ordering in the subscripts here. Notice if I do a partial of y to f first, then do a partial with x, the ordering on the subscripts is the direction that we read it, fyx, is actually the order I'm doing the derivatives in. Whereas when you do the operator version, right, it's whatever is acting directly next to it, right? So the derivative of y is directly on the f. So the y went first. Vice versa over here, partial with respect to x was directly on the f, so that went first. Notice the x is first, okay? And it doesn't have to be just second derivative here. You can do f, x, x, y, y, x, or any combination therein of those, right? You can do fifth and sixth generation derivatives, whatever, and any combination of the different directions. By the way, all of these derivatives work in higher number of variables as well. Okay, we'll see that again too. So example, a sub yx of xy. Okay, so over here I'm using this same a function, and what this is asking me to do is take a second generation derivative, a second level of derivative, on something that has already had a derivative, and it's a combo. What is this telling me? It's telling me take the y derivative first, then take an x derivative of that result. Okay? and something that already had a y partial derivative. Well, I've already got that. I've got a y derivative. Next, I should take the partial derivative with respect to x of that, right? So a sub yx is going to be the partial with respect to x of this 10y over x squared plus y squared. Okay? So I'm taking a partial with respect to x of this. So then next I will have to do a quotient rule now here, right? Well, no, I won't, because look, partial with respect to x doesn't affect y. So I can actually get away on this one with doing something like this. Look, I can cheat a little bit. Partial with respect to x of 10y times x squared plus y squared to the negative 1. Whoops. Let's erase that. Right? Since there was no x here and I'm doing an x derivative, I could cheat a little bit by just making this a chain rule real quick. The 10y is just going to be along for the ride. I'll still have the x squared plus y squared to the negative 2 now, right? Because I'm going to do a power rule, so I'm going to drop a power. But that also means the negative 1 would need to multiply in front. And it's a chain rule. Derivative with respect to x of the inside is going to give me multiplication of another 2x. So this a sub yx is going to be equal to, I've got a 20xy with a negative, so negative 20xy over x squared plus y squared quantity squared, because a negative exponent, I just move it back down again, right? Or you could have done a quotient rule, but I want you to note that the partial derivative with respect to x of the numerator is 0 in this case. Okay? Let's try another one here. I've got a sub yy, which means second derivative with another y derivative, right? On top of something that already had a partial derivative with respect to y. So I'm going to be taking the ay again, and then I'm going to be doing another y partial derivative to it. So that would be like this. I'm going to do the partial derivative with respect to y of ay. That just happens to be the same thing that we were just doing the partial of, right? Difference this time is the y derivative can now affect the numerator, right? That's actually a function of y. So in this case, I'm going to go ahead and leave it in quotient rule format. Let's do that. So low d high, here's low, derivative of high is 10, minus high d low, 10y. Derivative of the bottom is just 2y. Over square of what's below. Okay? So in my numerator, I've got negative 20y squared right here, right? And I've got 10x squared and 10y squared. So 10x squared plus 10y squared minus 20y squared all over this thing squared. Right? Okay. So let's factor a little bit here. I'm going to have 10x squared minus 10y squared over x squared plus y squared quantity squared. And of course, I could factor the numerator out by pulling a common 10 out, and then it would be a difference of squares with x plus y and x minus y. But none of those binomials are going to be the same as this binomial. So unless you're solving, which later on we will be, but in this case I'll stop here because I don't need to solve or factor or do anything to simplify. So that's as far as that one needs to go in this case. Okay? So you can have second partial derivatives, you can have third partial derivatives, you can keep going with this. Okay? The next thing I want to show you is that also, if the function is continuous, the order in which you do these is not going to matter. So to continue the conversation that we were just having about second partial derivatives, I want to expand a little bit more on the idea that the crossover derivatives will be equal to each other. Okay? So in other words, the yx, right, partial with y, then partial with x, will be equal to a with the partial of x first, then the partial of y after. And in the case that happens, what it turns out is that as long as the function is continuous on an open set containing whatever points that you're wanting the two derivatives to be equal to each other, okay? As long as it's continuous on some open set, basically, you know how continuity works. It has to have all of the different directions with the limits, and you have to have it in some open set around, and then the epsilons and the deltas shrink inside of that open set. So basically, if f is continuous in the region that you're interested in, then the second derivatives, in fact, any level of derivatives, third, fourth, whatever, and any combination you want to put in there, are going to be equal to each other. It's just that with a lot of the derivatives we'll be doing, typically we don't go much further, if at all, past second derivative. And this is the one we end up hitting a lot, especially later on with our optimization. Our mixture derivatives, it doesn't matter what order you do them in, you're going to get the same result either way. Okay, so let's hit this example right here. We just did these two partial derivatives here, the second partials. Okay, we just did those. An exercise for you to try. Notice the AXX, the partial with x, then partial with x again, is very similar to the double partial with y, except look at where the subtraction is going, right? The y squared is first, the x squared is second, and vice versa here. This is the one we already did, and using that same idea of quotient rule, okay? When you do your derivative of the x one with an x again, you should notice how you'll get this same thing, but the y in front instead of the x in front, okay? Now, to show you the crossover ones, right? We did this one already. I did the x derivative of the a partial with y already. So now, to do the axy, I will do the y partial derivative of the ax function here. Okay, so look, partial with respect to y of 10x over x squared plus y squared. Okay, and you remember the workaround that we had before was we're doing the partial with respect to y, and the numerator doesn't have any y's in it. So I can pull that fast maneuver that we had last time. So it's 10x times x squared plus y squared to the negative 1. And I can do that derivative just with a quick chain rule where I drop the negative 1. My 10x is unaffected because it's just going to be a following constant. I leave the inside alone to the negative 2 power because of the power rule, times the inside derivative with respect to y gives me 2y there. Okay, so then I rearrange this again, and I'm going to put it up here for us. I'll have negative 10 times 2 is negative 20 xy over the x squared plus y squared in the denominator here because of the negative power to the second. So you'll notice that these two are equal. Except, where are they not equal? Right? Those two, you can see they're the same function, right? So you're saying, wait a minute, Professor Simon, those are equal everywhere. No. You're skipping something, right? What about the point where x and y are both 0, the origin 0, 0, right? You get a division by 0 in both cases, okay? the derivatives are undefined there. And sure, they're both undefined. That doesn't mean they're equal, okay? They're both undefined, which means they both don't have a value there, which means they are not equal at 0, 0, okay? So just a quick side note, these two are equal. AYX equals AXY everywhere except 0, 0. So notice also the original function here is not continuous, right? Discontinuous at xy equals 0, 0. This is one of those revolution functions. Remember the ln of the x squared plus y squared is the funnel looking shape, because you have your logarithm shape and then it's spun around, right? Looks like a funnel, and it goes infinitely down and never makes it to 0, 0. You have that discontinuity at 0, 0, but it's continuous everywhere else. And notice your second mixture partial derivatives there, right? This guy and this guy are completely equal everywhere else other than 0, 0. They're both undefined at 0, 0 because all your derivatives are undefined there. All of them are, right? But it goes to the point, right? The two crossover derivatives are going to be equal whenever the function is continuous. And later on, that's actually a useful tool in reverse. If we take our second partial derivatives and we show that they're both equal, then we can point out places where the function is continuous, because this is a two-way street, right? If it's continuous, then the second partial mixture derivative functions will be equal, or if the second derivative functions are equal, then the function is continuous, okay? Another point along the same lines here, I can do all of these partial derivatives to functions with 3 variables, 4 variables, 5 variables. Partial derivatives are that, precise and that useful that it doesn't matter how many variables you've got, because that just means I'll be holding all of the rest constant. And this rule still works with higher dimensions as well, okay? For example, let's take a few partial derivatives here. What would the partial derivative of f with respect to x be? Go through the list here. I would have 3z squared, right? Because the derivative of x is 1. This would be 0, so that's gone. And then here, I would do my power rule, and the sign of z is constant. That's just along for the ride. So I'll have minus 6x squared sine z, right? Okay. Now do f sub z. In other words, the partial derivative of f with respect to z, right? Okay. So right here, the 3x is along for the ride. Derivative of z squared is 2z. So I'll have 6xz. Derivative with respect to z here is going to be plus 4y squared. And derivative with respect to z here is going to be minus 2x cubed cosine z. Okay. Now do fxz. That's going to be the derivative of this, but now partially with respect to z. So this has a z, that's going to give me 6z, right? Here, derivative with respect to z, the 6x squared is along for the ride. I'll have minus 6x squared cosine z. Over here, derivative f of zx. So that's the partial derivative with respect to x of the f sub z function here. So derivative with respect to x is 1, so I'm left with 6z. No x's here, so it's 0. Here the cosine z is held constant, So derivative of 2x cubed will give me minus 6x squared cosine z. So what you'll notice is these two are equal. Yet again, right? And from the original function, you'll notice it's continuous everywhere, right? It's defined everywhere in 3 space. Every point in 3 space works for all of these functions. There are no discontinuities in this function. So, and you'll notice these two are equal and work everywhere. And they're completely equal everywhere, completely continuous everywhere. Okay? So you can take partial derivatives of any size function with any number of variables, all right? That doesn't change the definition of what a partial derivative is. And any combination of second derivatives, mixture ones, not like xx and yy. Any mixture second derivatives are going to be equal whenever the function is continuous. So I hope this has helped you understand the derivative process that we're going to start with multivariable functions. Next, we're going to build up on chain rule and differentials, and eventually the big whopper of the gradient, which we use like a derivative with multivariable functions. Stay tuned for those.